Okay, so today we're going to look at algorithms and the big O notations, and specifically two types of algorithms are the search and the sort algorithms. We're going to look at that today. Okay. Firstly, this is the outline we have. In terms of the search algorithms, we'll look at the linear search and the binary search, and we'll talk about what the algorithm complexity efficiency marker is, also known as the big O notation, and also look at three sorting algorithms: the select sort, insert sort, and the merge sort. And like always, I might switch from NetBeans to the slide just so I can explain certain concepts that will give you a better understanding of what we are trying to do. All right. Before we even jump into what searching and sorting is, we need to know that the reason why we're interested about algorithms is because we want to have efficiency. You want to have an efficient system. When you're designing your code, you want your code to run smoothly, have less complexity as much as possible, or rather, I might say we need a way by which we can measure how efficient our programs are, all right? And the way to measure that level of efficiency is by looking at it in terms of complexity, right? There's usually a trade-off that has to do with how fast your program runs, all right? How much memory it occupies during that run, and basically how efficient it is. And the way we can gauge that is by using the big O notation. And I think that's where we should start from before we even begin to look at what algorithms are. And still pointing to that, we see that your algorithms are going to be using, or are going to be operating in specific data structures, right? And data structure is basically a way by which your data is arranged in the system, either linear, sequentially, or any other format. But based on data structure, we see that we now have algorithms that handle that data. And since they handle the data, we now have to find a way to see, is it efficient in handling this data? Now, I can give you a task, all of you right now, and say, write me a program that allows a user to pick a cup from point A and put it in point B. And I can get, if you're 100 of you here, probably I can get like 80 different ways you can do that. But how I would score is based on efficiency. So using the big O notation, we can now score how efficient were the programs, or whose is more efficient than the other, things like that, right? So going forward, in case you hear things like big O notation, what they're referring to is the complexity of your algorithms in terms of how it works in the time domain and how it works in space, all right? Okay, let's see. Okay, just give me 1 minute. I would like to start from here, but I think there's still some groundwork we need to do before we start jumping onto this space. Let me just quickly shift now. All right, I hope this is clear enough. Let's see. So algorithms are basically step-by-step procedures for solving a specific problem, all right? And when we ask you move the cup from point A to point B, it means that we want you to list out how you're going to take that initiative. Remember when you did C programming, we said C programming was procedural. What does that mean? It means that you must specify each line of instructions that must take place from point A to point B. And that's basically what an algorithm is. You've written some, and I think we introduced some to you when we did software design 1, where we showed you some algorithms and that can run specific kinds of code. It's the same thing we're talking about. But in this case, even though algorithms can be interpreted in pseudocode, where we have some instructions that tells you what happens step by step, the efficiency is what we now we now call to question in this study, right? Okay, so here we say the same problem can be applied in any number of ways, whether you're doing searching or sorting or routing or scheduling, encrypting, learning, whatever it is. But the algorithms will have different approaches, therefore have different performance and different trade-offs. The things we look about, we try to look at is how do you measure efficiency, or how do you measure performance, sorry, and that's based on complexity and efficiency. Now, the BigO notation indicates the worst case for an algorithm. It always indicates the worst case for an algorithm. So how bad will it take for this algorithm to run? What will it take? That's the right word. What will it take for this algorithm to run? Will it take much space in memory? Will it take much time to compile? All right. So that's how we measure that. So we look at that in terms of complexity. Two complexities are shown here: the time complexity and the space complexity. Time complexity tells you how many number of steps will it grow for a given input n. All right. So it looks at an input n and see how many times to run that in a loop. Right. The time it takes to run that is time complexity. Second one is space complexity. How many extra memory will it require? So basically, how does it grow in terms of its consumption of memory? All right, and that specifically speaks to some data structures like your arrays, that with every change, you probably have to allocate a new memory block for those contiguous memories. All right. Okay. Some examples of these will be your O, and the O there speaks to the order of. All right. So if you see the first one, we have O of 1. It speaks to the fact that we're having just one constant work. It means that when we perform that algorithm, it's probably nothing rigorous for us to do repeatedly. One run, it gives us the outcome, right? So for instance, if I say print hello world, one line doesn't take you much. So there's no, just in constant time, that output is given to you. The next one grows by the order of n, O of n. And that one grows with a list length. So basically, if you're dealing with an array, unlike when you're printing just one variable information, now you have to run through the number of elements in that array. And that number of elements is what? N, remember? So it means order of n tells you that this is by how complex it's going to be, because you have to run that through a loop to give you some desired output. The next one there is O to the n squared. And that grows by the squares, or that grows by the squares of n. So the variable n now has some power by which you have to consider in its operation, and that tells you the level of complexity. In fact, all these ones you see, log of n, n log of n, they are even more. This is just a few of them. There's a list, the link I have there, where you can go and look up all the complexities you have. But just to give you how algorithms are measured, when you write your code, sometimes I see you use for loops, you use while loops, you use do while loops, you use recursive statements and all that. But if you measure time, it tells us if we keep running this loop over and over, how many loops will it take for this algorithm to be completed? And that will now tell us, in terms of time complexity, how long or how efficient your algorithm is. If in terms of space, how much memory will you require each time you run that loop, or each time you run that program? That's really complexity in terms of space. Either way, you have the O complexity or the BigO notation to symbolize which is which, right? Okay. Just to give you some examples there, we have this. So the first one, we say O of n, the time doubles. The next one, you say O of n squared, it means that it goes almost 4 times. Then log of n just means that it moves one extra step forward. And n log of n tells you that a bit more than just double. So it doubles, but more than a bit more. And we can see that from the small table I tried to create in this slide here. If you look at the type of complexity, one is considered a linear time complexity. And with this one, you move n steps here. And if n was 2 to the power of 10, which is 1024, you see that you have 2 of n will be this amount, meaning that the change is twice the original size. So imagine it takes you 1024 milliseconds or seconds. Let me use that word so I can find a unified unit, all right, to run that. And you're going to do that twice. You can gauge how long it will take you in terms of time. Now, if that's our base, we can now look at when we have a quadratic type that has n squared. What happens? You see the number of steps it requires n to the square, and that value of 1024 now become over a million in terms of seconds to run, right? And to n of that even goes even higher, and it shows you the changes it has. Whichever type you have, whether it's linear, quadratic, logarithmic, you have that level of change that occurs each time. All right, and this is how we measure complexity in terms of time. All right, in that example. Okay, now just so that you have more than what the slide is giving to you, there's a link here that I'll keep when I upload this information. You can visit that. In fact, I think I can open it up now if I'm able to, so that we can see what it has. Is it? All right, so this tries to explain the BigONotation tutorial, giving you a guide to what BigONotation analysis is all about. All right, in here, it gives you more descriptions as to what to expect when analyzing the BigONotation. Even gives you some instances of them and the example. Quickly, let me just run to a graph I saw here that explains something. See here? Yeah. So this is a plot that tries to explain the runtime of different algorithms and how it translates in terms of a call, level of complexity. So what you want your algorithm to be is somewhere within this region here. N to the order of O to the order of O to N or O to log of N. It's good. It means that it takes one step, maybe a few steps for that to complete. But we know that that's not always the case because our problem sets are quite different. So depending on the problem set you're dealing with, you can easily see the complexity of your algorithm rise exponentially. All right. So if in case you want to know more, this website has some code with various examples of each and every one of them. You can try it out at your leisure and just play around with it and see how to estimate the big order notation for several types of algorithms. So when you see something similar to your work, you can now know exactly what order of BigONotation you have or you're dealing with, whether it's n log of n or log of n or O to n squared or just O to 1, right? And things like that. Okay. All right, so that's now we can now go back to the main discourse, which is algorithms. And like I said, there are two types you're looking at: the searching and the sorting, and the examples that we'll look at within these categories. But now we can now see, when we now say, okay, this particular one has the order of this, you'll be able to relate to what we mean by that, because that's exactly what the BigONotation is trying to do. For the search algorithm, it involves determining whether a value search key is present in a specific data collection. All right. So if it's present, you're able to now determine where that would be within that data collection. So we assume in the example here that, okay, let's say we're dealing with the first kind of searching algorithm that has to do with your linear search. So in your linear search, it is simple, quite slow in terms of what it provides to you, but it's very simple. All right. It gives you less complexity because you're just going linearly within that search. The algorithm here is shown for each and every example I provide, just to see what the pseudocode will represent. So I show you the pseudocode, then we'll now do an example with that so you can see how it performs. Right? So in terms of linear search, assuming our function linear search has two input arguments, A and key, where A is an array, And key is our value of interest that is contained within that data collection, that array. If we run a loop from where I is 0 and goes up to the length of A minus 1, and within there, we now keep searching element-wise where if A is equals to key. All right, so if A is equals to key, then we return 1, otherwise we return 0. This algorithm is a simple algorithm for linear search. You can all relate to this because we do it all the time without even realizing it. What is going to return back to you here will be the index of where the key value is contained within your data structure. Is it clear? Okay. Now, if you want to look at it numerically, let's see this here. All right. So we have A, and it has an array 18, 7, 42, 13, and the key value there we're looking for is 42. It means that when we run that algorithm I just showed you, where we go look by comparing the elements in 1 over the elements of all, we'll be able to easily identify that the first 2 elements are not the key. We'll get to 10 elements to return 2 for us. Why does it return 2? Why does it return 2? 1, 2, 3, minus 1. Yes. Yeah. Yeah. You get, yeah. So what he's saying is right. So basically, he's looking at the index and returning that back to us. So if we go and the index of the array 0, 1, 2, where we picked up 42 or where the key exists is in index 2, and like I said, it returns back the index to us. So we get 2 there. So in terms of complexity, you get the time complexity to be O to the order of n, and the space complexity to be what? O to the order of 1. What's the difference?
What's the difference?
Yes. The time and space complexity. Why is it order of O, order of n, and order of 1?
You're not creating just the key, which is 1, they were taking up more space.
Good. So there's no more space. So since we don't demand more memory, we see that we have to the order of 1. It's constant, so there's no change. O to the order of n, why do we have that?
As the array increases, the search time increases.
Yeah, but in this case, we're not searching. We're just going through. We're comparing the elements, right? So we're running the loop. So the loop goes element-wise. I explained that already. So n starts from 1 in the first variable, but it easily increases to 2, 3, and so on. So we have n there. Is it clear?
Yes.
Okay. The next example we have is the binary search. So the binary search here allows you to also compare the elements within your program. So here it gives you more faster results, but also more complex. Again, if A is a sorted array in an ascending order, all right, and we take in 2 variables. Yes?
Oh, sorry, so I want to go back to the other one. If you used n squared, what would happen? Would it skip an element to speed up the process of searching, or what?
No. We're only using you're only using the big O notations to identify the complexity of the algorithm. The n has nothing to do with that. Right? When I say what's the time complexity, I'm just saying identify what you see in terms of the loops. Remember, let me just go up so that I can clarify this in case there's another person having an issue. Well, when we're here, where is it?
So the big O has nothing to do with how doing the search. It just shows us how it's searched.
It tells us the states of our algorithm. It has nothing to do with how it searches. It's based on the performance of the algorithm that will now identify what the BigONotation will be. All right, it's a way to measure the complexity of the algorithm. Do you get it? So the example I gave earlier was that if I say print a statement hello world, all right, print hello world will require no loop to do this. 1-line statement is gone. So it means order is what? O of what? 1. It's much easier. But if I say print the elements contained in an array, maybe a 5-element array, all right, you know that if I was printing the first elements here, which would be order of 1, but in this case it's an array, it's continuous memory block. We have more elements. So you have to traverse through that data structure, and to do so, this becomes order of n. So in that case, because we are inspecting each block to identify where the key exists there and return the index, and that would be go to the order of n. Yes.
So whenever we're using arrays, we're always going to use n because we're going to move one at a time.
Yes, and whenever you're dealing with an array, you always have the order of n, right? And because you use a loop, and again, it depends. I won't say whenever I deal with an array. I would say depending on the operation you're performing on that specific array. That's the right answer to say. Because if the operation is more complex than this, then you probably have an exponential or a logarithmic or some kind of complexity popping up there. All right. Okay. Let's continue. So the binary search here, we have some variables to begin with, signified as our low, which is 0, and our high, which is the length of A of 1, where A is still our array. If we have two parameters in that algorithm, because the first thing I'm showing is an algorithm here, so please just take note of that, all right? It's an algorithm so that when I show the numeric operation underneath, you understand how that happens, right? And the algorithm says if a binary search has two parameters, the array and the key we're looking for, similar to what we did in linear search, all right? While low, which is 0, is less than high, which is the last element you're looking for, perform this operation. This here tries to create a midpoint where we take into consideration where the high and low points are, right? Then if A mid is equals to key, so in essence, we are dividing the array structure into two and say, okay, this particular point you chosen here, if this is equals to the key, then return that we found what key is. Quite easy. Else, if it's not, then compare if that midpoint is less than the key value. If it's less than the key value, what do? You now say low is equals to the midpoint plus 1. In other words, you're going to be increasing the low points coming up, right? Else, if it's the other way around, then to be high is equals to midpoint minus 1, means you're going to be decreasing the midpoints coming down. Either way, you're going to try to search. You have this block into two parts, left and right. And if you say, if this is where it is, come up slowly until you find where the key is. If this is where it is, come down slowly until you find where the key is. You get it?
Sir,
yes.
Does this mean you can only use this with sorted data?
Yes, which is why I was using that. It must be sorted in ascending order. All right. In this case, you're only trying to inspect. You're not trying to sort. Remember, you're just searching. That's the idea.
So it must be sorted correct.
It must be sorted. If you want to perform sorting, we have the examples down and you see that. In this case, all you're doing is just searching the array or searching your data structure to see where it is. Right? Okay. At the end of the while, we return the -1 if it's not been found. It means that the key doesn't exist within that program. The example we have here is shown here. So if A is our array as given as this, 3, 8, 12, 20, 27, 31, and 42, and the key we're looking for is 27, right? So we perform the operation mid at index 3. So 0, 1, 2, 3. Index 3 is here, so that's 20. Right? So we compare, is 20 less than the key we're looking for, right? If it is, then we search the right half. If it's 20 less than or greater than the key we're looking for, if it is, then search the left half. Then mid at index 4 will now be 0, 1, 2, 3, 4 will now be here. So if this is found here, then we say index 4 is the answer, right? So in other words, we search the sign greater or less, wherever it falls under, we go up or we come down, like I explained to you on the board.
So right? You determine your mid, or you just use the formula to find it?
We just use the formula to get the middle. Right? The formula was shown to you, right?
Because you have different indexes. That's what I was asking.
Yeah. So this is just a simplified form to show in numbers what's happening up here. So in case you're not sure, just always look up here and see what's happening. But to make it very easy, what we did was that we gave more than enough numbers. So we can say the middle here is what? 20. Right? So all we have here, you know this is not the one. So we have 8, 2, 8, and 12. While here we have what? 27, 31, and 42. So we can either search left space or we search the right space based on the condition we stated here, this key condition stated here. And then you find what the key value is. Yes.
So let's say your array has like an index of its index is odd. It's even, sorry, it's even. So does it go in?
You floor it. So you're going to floor this so that it takes a one-sided. Do you understand?
Okay. Oh.
Yeah. So if you're having like you're having like say 4 variables, all right? If you floor it, it means that you have 1 here and 3 there. You get it? But you still have to search it out.
Okay.
Yeah. Okay. Are we together?
Yes.
Anybody confused so far? No? You're together? Okay, let's continue. Now, the reason why I'm going through here is because when we're done here, I'll now jump back into the slide. It now make more sense what's happening there. All right, in terms of example. Yes. So system's a bit slow. So the precondition for this is that it must be sorted. All right, and this gives you an order complexity of O log of n in terms of time. Why is that? It's because the search space itself is half into 2, right? And the space is still O of 1. Why? Because we're not allocating new memory, so the space still remains the same. All we're doing is just searching through that space to see that we find the key value that exists within that space, right? So that is the example for your searching. We have 2 examples, like I stated, the linear and the binary search, right? The next thing now is to look at the sorting algorithms. All right. So for sorting algorithms, we want we want to be able to have some data collection or some data collection, and want to be able to sort that out in a specific order. Right. So in an ascending order, if we have say all the test results from test 1, all right, given, and because of the way the students' numbers are, because of the probability of not having an ascending order, we'll have say 80, 12, 70, 35, and so on and so forth. But the idea is that we want to sort that out in some order. This sort algorithm comes into play. For the sort algorithm, we've been able to show, or what's been stated in the slide, is that there are 3 examples we look at: the selection sort, the insertion sort, and the merge sort. Each of them provides its own level of complexity. It means that when you're going to apply this, it depends on what you're trying to do and the complexity of the problem you're trying to solve. Right. Again, the variety of sorting algorithms can be used to achieve the same objectives. Right. All that matters is the level of complexity and efficiency that it provides. Right. Most times when we write programs, we don't think about efficiency. We just want to just get the job done. Like I said, if I give a task now, everybody does it. I'm done, sir. And we look, okay, it's okay, it works. But if we want to really go down to, okay, let's see the level of complexity that yours has, then we can measure in terms of efficiency who has the highest efficiency in terms of. One of the things I've learned as an experience is that it's best to work with vectorization. So vectorize the variables instead of writing it in loops. If you can deal with vectorization, then you minimize the number of loops you have to write, making your code more efficient. But I don't think we'll do that now. Yes?
So
what's that? It means that if you're able to deal with the numbers or that data set as a bulk sum, do that instead of dealing with individually. So what we're doing here in your loop, right, in the arrays, and we're working with scalar values. So we take one element at a time and perform some operations with that. But the cases whereby you cannot work with everything, you can work with the entire block by doing some manipulation, some matrix manipulation, your dot operators. You just perform some operation at the same time with all the variables and get that sorted out. All right. The examples I have for that are not in Java. All right. I'll probably show you some examples, but they're not in Java. That's it. Okay. Again, let's look at our sort selection example here. We have the sort. The main thing about the sort is that it's able to exchange the content of 2 positions. It uses a swap operation and not a shift operation. And I'll explain that when we get to that point. So let's say if n is the length of A, so it means that n has the entire number of elements contained in array A or in data structure A. If we now fit A as our only input in our selection sort algorithm, we perform these operations. Notice that from line 93 to wherever it ends in 100 there, you can identify two loops running in there. The first loop is when I goes from 0 to n minus 1. And in there, all we're trying to do is to identify an index. That IDX is basically like an index that holds the value of I, whatever the value of I is, it takes that in. Then in the inner loop, which starts at line 95, we say if j goes from I plus 1 to n minus 1, to n minus 1, yes, do this. So if we now have a of j, which is a or whatever the inner loop is, remember for this one, it takes into consideration what a value of I is plus 1. So if I is 0, j will be what? 1. So in other words, you're looking at some array, index 0, 1, 2, 3, 4, 5, 6 in this case. So if the value of I is at 0, the value of j is at what? It's at 1. So that operation. That's what we are saying there. Okay. All right. So we now compare if a of j is less than a of idx, and idx is the same thing as index I. All right. Then do this. In other words, what he's saying is that if I have 2 here and I have 5 here, I'm comparing these two together. I'm going to see which is less than, which is greater than, and perform the given operation underneath there. All right. So what's the operation? If this is true, then idxj or idx should be equal to j, right? And if, then we n4, then outside here we now swap a of I with a of idx. So if it's true that the one here is smaller than the one here, so the example would have been best by doing this. If we have 2 and we have, if we have 5 and we have 2 here, and we compare these two elements, and this is smaller than this, perform a swap, and that's what's happening at this point here when that swap performs. So imagine you have, say, 7, 3, 1, 8, 4. Yeah. If you compare each of them and perform swaps, as long as this line is true. You get that? Are we together?
Yes,
Okay.
sir.
So remember, we started by saying I is 0, j is 1. So when we move and I is now 1, j will be what? 2. So we keep moving in that capacity until we get to the very end. And as it moves, it performs a swap. So a swap doesn't require an extra memory location. You're just taking the element that's contained in one, putting it in another, and taking the other one and putting it in another. So they're just swapping positions, but the array still remains the same. No new arrays created. Okay. So in this case, if we were to perform that, we'll have at this operation here, 2 and 5 will swap. Then now 5 is now here. So 5 and 7 will check. It's not true. We leave that, go to the next one. We see that it's true, so it's swap, right? So now be what? 3 and 7. We come here and check now. 7 is now here. We swap again. So now be what? 1.
So it's actually doing bubble sort now and not selection sort. Selection sort goes to the whole array.
Oh, sorry.
Finds the
Sorry.
Finds the smallest, and that index gets.
Bubble sort is my favorite. I'm sorry. All right. Well, yes. In this case, we go through we take one and go through the entire loop first, then come back again through the entire loop. So it's the same thing we're doing, but in this case, I was doing it individually. Well, he's saying that we take one and go through the entire loop, take another one, then go through the entire loop. That's what this one is saying. But bubble sort, which I didn't put up as an example, unfortunately, we'll take it pair by pair. These two pair deal, these two pair deal. We'll keep doing that until everything is sorted out. All right. Sorry for the confusion, guys. All right. Okay. Let's look at some numbers. Numbers will make it much easier to understand. Okay, yeah. Okay. So here we have 29, 10, 14, 37, and 13. So if we try the first one, when I is equal to 0, we'll be able to identify that 10 needs to be swapped. So we'll swap that out there, and we'll have 10, 29, 14, 37, 13. We keep doing the operation and keep performing the swap. The next smallest one there will be 13, and it will move to the position where it's meant to move. The next smallest one there will be 14, But 14 will stay where it is because there is no change. It's in its right position. And the last one there will be 29. That will move from the very last element to the second to the last position. And we have a sorted array 10, 13, 14, 29, and 37. All right? Again, we'll do examples of that, so we'll see more. Time complexity now is O(n) squared. All right? Dealing with the fact that we have multiple loops or nested loops in that operation. Then notice that space. You have a question? Notice that space is still O of 1. Why is that? Because we're not allocating new memory. We're still using same memory, just swapping out the elements in their positions. All right. Okay. Let's look at insertion now. So unlike the selection sort, the insertion sort is not performing a swap, it's performing a shift operation, meaning that it's going to be shifting blocks, all right? And insertion, like the name suggests, is the fact that I have the ability to fix in something into a specific location, all right? So remember, if this was our array, or if this is our array, where we have 5, 2, 7, 3, 1, 8, 4, all right, and when to insert a new one in the middle here, say 13, all right, it means that we should be able to perform some operation that allows us to insert that information. The ability if you try to change the state of an array, what the compiler does, like I explained to you when we're doing C, is that it will leave this one, create a copy of that with the changes you've made. In other words, allocating new memory with the inclusion of whatever you're trying to add inside there. It takes up space. Do you understand that? Yes. Anytime you try to perform an insertion with an array, it creates a new data frame completely, a new data structure completely with the changes you've written. It is not the same. Right? Yes.
Is there no way to use like your
There's no way to do that. I'm telling you, for an array, the only way you can do that is in a list. With a list, you can append to a list, you can add to the list. With an array, it's fixed. Once it's created, it's created. If you make any adjustments to that, it creates a new location, a new memory frame for you, for that to happen. Right? Okay. Let's look at the example. If n is equal to the length of a again, we're passing a as the only parameter or the only input argument to the insertion sort. We have for I from 1 to n minus 1, they perform this. So the key is equal to a of I, so we selected our key, and j is equal to 1 I minus 1. So while j is greater than 0 and a of j is greater than key, then perform the following operation. All right. So the operation is what? Let's a j plus 1 is equals to a of j, and then decrement j. J is equals to j minus 1. Who can explain what's happening here? Yes, go ahead.
So I'm guessing, but wouldn't it be extending the array by because you're creating a new array by extending it by saying aj?
You're picking my words now. Explain the operation happening here. That's what I'm saying.
Or it's creating a new array by extending it, but then it's to get it.
Okay, where is it creating the array? Come and show me where it's creating.
By while j is created. So the a j plus 1.
What line is that?
Line 118.
118, this one. Okay, you're saying what?
That it's extending the array in order for you to insert whatever you want to by saying now this new one is going to equal to the aj. Right?
I don't even know what to say. It's a good attempt, but who else can try? Guys, try. Let's look at the algorithm. I've already explained about 3 to you now, so you should be able to see what you're saying and tell me what's happening. Just explain what's happening in this algorithm. If I gave this algorithm in a test and I say explain what's happening here, what should you say? Just think about it for a minute or two and let me know what you say. Hold on, you had an attempt. One more minute.
Okay, our next step is as you increasing, is comparing actually J is decreasing, so that's certain as well as if the current one, it's almost like bubble sort where it's inserting into the previous one. It's searching, it's going backwards. And if that current one is less than the previous one, it's taking that one and putting in that one. So it's I don't know why it's called insert search. It doesn't make sense.
That's his conclusion at the end of the day. Any other person try? You want to say something?
I want to see if I can edit because you said you explained it by saying an array. What's an array is made? It's already fixed.
I know that. Just explain what's happening here. Don't tell me. I know that.
So my guess is that it's since the key is AI, the key that you're trying to insert.
Go ahead. I'm
guessing that the key that you're trying to insert is AI, but then to find that index, the index is J.
Okay.
And then from that index, you add on, I think, another element into the array to create a new array, which is AJ. And then to find the index of that key inside that new AJ is J minus 1.
Okay, usually when you have something like this, just you know about arrays and indexes, just put in the index where it's meant to be and just investigate from that point if you're not sure, instead of guessing. All right. So the algorithm says that from I starts from what position? From 1. So this is 0, 1, 2, 3, 4, 5, 6. So this will be your I, right? That's the initial one. Okay. So if I is that, the value of interest, which is A of I from line 116, will be what? 2, right? So this is 2. That's it there. Okay. Then the next one is what? J. J is equal to what? I minus 1. So if I is 1, J is what? 0. This is J here. So A of J will be equal to what? 5. Right. Okay. So while J is greater than 0, greater than equal to 0, sorry, and A of J is greater than key. So again, we've picked out the key. The key is what? Is this one, right? So if this A of J is greater than this one, what do? We now do what?
You always loop until you reach 0.
Exactly. Yeah. So in this case, the while there, within that while, what do? AJ1 is taking this position here, which is your 2, and it's making it equal to what? Your 5. So the new position now is basically saying that this is what? 5. That's what's happening there. All right. Then J is equal to J minus 1. All right. So if J is 0, the loop stops. All right, and that loop terminates. So all we've done in that space is just say, if this is greater than this, move forward. That's happening there. Then the next thing here we are doing here is that back where we have here, remember J is now less than 0, we plus 1 to that is now what? Back to 0 equals to key. And the key is what? 2. So we're basically just swapping 5 and 2. Yeah.
Let's do another one. Let's say A is 4 now.
Yeah.
And then what happens? Let's say I is equal to 4. We have 4 now.
Where is it? Are you here?
Yeah, let's say I is
Okay.
now.
So I is equals to 4. That means J will be equals to 3. That operation. Okay. So in there, what happens? We compare that. We say is what? Is j greater than 0? It is. Greater than equals to 0? It is. And is j greater than equal to key? The key is what? The key is 2. All right. So if 3 is greater than 2, or okay, let me put it like this. Let me not say the key is 2 because the position of the key changes each time with the loop. All right. So when this is equals to 1, when this is I, the key will be what? 1. So the key.
Because I never saw the key change.
Yeah, see the key here.
Yeah, but where does it change? Oh, as I increases.
As I increases, yeah. So if this is your I, it means the new key is what? 1 in this case. So you're still again going to swap rows as long as this is greater than this. The operation itself is a shifting operation, not a swapping operation, because you're shifting positions here. And because of that, you're going to be creating new array each time. The insertion you're talking about is easier to picture when you're adding a new element, appending a new element to this. That's still insertion, right? But this operation as well is considered different from selection sort, where selection sort just swaps the elements as contained. This one actually takes one off, because if you look within this loop, we're taking it off completely. So in that space, what we have here is 5 and 5, first space. But when we leave that loop, is when we now append 2 in here. Do you get that? Do you see that? Talking to you. It's a bit tricky. Don't worry. When you go back, watch the video again, maybe, watch the class, maybe it will be much easier for you. Again, we have a for and a while. The while loop only terminates when j is less than 0, right? So in here, what we're doing is that we're replacing the value of I. We would have as well written a of I, but we said a j plus 1, so that the position of, let's say, move it one position ahead, which is where I is. So whatever was in the previous one, put it here. So in this line here, that in essence, deleting, this was 5 initially and 2, we are deleting 2 and popping 5 in there, in that space. Then when we finish the while loop, when we leave that space, that is when we now insert 2 in the space. All right? Question? Every time it does that, it creates a new one, which is why it takes up memory. So the order of space you have is based on the order of elements you have in your array. All right? All right. Let's look at this. We have 5, 2, 4, 6, 1, 3. We're performing the same operation here. So we compare if the key is 2 here, right? And this is your j, this is your j, this is your I. What happens? Notice that 2 is gone completely. We have 5, 5. 2 was basically erased. The data was erased, right? So we now place it back. When we leave that while loop, and we now see 2 coming here. So in other words, we're inserting 2 back into, using as a key back into the array. We keep performing that until we get to the end there. The order of operation, because we have 2 loops embedded in each other, is O n of n squared, and we now have a space that is what? O to the order of what? N. Why is the order of n? Because each time it keeps making changes, modifications, requiring new memory, because of the fact that the elements are being inserted back into the array. Is it clear? Alan is like, no, it's not clear. All right. We'll revisit this if it's not clear one more time, but let's move on for now. So the last one here is the last example we have, which is the merge sort. So this one, are you having a different class? You shouldn't sit there. It's not a good combination. Okay, let's continue. Here we have your merge sorts. Within the merge sort, you have algorithm that takes in. We have 2 algorithms running here. The first algorithm deals with the subarrays, and the last algorithm deals with the full array. All right. So the subarray here takes in one input, which is your array list of A. What it does here is that it compares if the length of A is less than 1. All right. If it's less than 1, then it returns A back and ends the if. All right. The reason is because we're going to be performing your split again, the operation. So you keep splitting that until we get to the position whereby the length of A can actually be less than or equal to 1, sorry, not less than 1, less than equal to 1. Okay, so how do we perform that split? We perform that operation again where we now floor the length of A divided by 2. So in case that thing happens where you say, okay, if it's even, what do you do? There's a floor there to show in this case that we're going to take one-sided operation of that. And we're going to have 2 components, 2 parts. Your left sub-array and your right sub-array, like the example I had before earlier. Right. We're going to merge sort them. So what does this line remind us of? Yes, it's a recursive call. All right, so it's calling itself to perform the operation for L and for R. To keep doing this same operation over and over and over until it gets to lower components. Then we end the aberrant. So this is the first part of the merge sort that deals with those sub-arrays. And the next one underneath there, too far. Okay. The next one here deals with your merge. Here now has your sub-arrays as its inputs, the left and the right. What's happening here is that you have a while loop that says while I is less than the length of whatever is in the left subarray, and while j is less than the length of whatever is in the right subarray, then perform the following operations. If the element of the left subarray is less than that of the right subarray, then append to the position of the left subarray, take that information and append it to t. So we append it to t, then we now say I is equal to I plus 1. This is basically an increment like saying I plus plus, all right? So it means that if we compare these two, I have divided my array into 2 parts. The first part is here. It has a 2, 5, 7. Okay, the second part is here. It has, say, 3, 1, 8, and 4. Something like this, all right? This is my left. This is my right. All right? My n of I will be at this position because I starts from 0, j starts from 0. And my r of I will be at this position again because j also starts from 0. So this is now used to compare the elements together. So we said if 2 is less than equal to 3, then let what? Let the position of 2 be fed to a list called t. So if t was some list, it means that t, and just represents as an array in this case, right? Will have its first position here with the number 2, so it is smaller than the rest there. We keep repeating that process. If r is the one that is smaller, then we put in r there. So if this was smaller, it would have been here, it's smaller. So we're basically just comparing those information and merging together to form a new list that is now appended or returned at the end of the program here. You get that? It's clear, right? This one's not stressful. Yes.
Because it moved from index 0, index 1, index 2. So what happens if the number in index 1 is greater than the number in index 5 of the right hand side?
Index 1 greater than index 5.
Yeah. Like because it's going like index 0 for both, and then index 1 for both, index 2 for both. Doesn't it check index 0 compared to all the indexes in the right hand side, and then check index 1 compared to all the indexes?
Okay, so what this one is doing is that you're just comparing them in this way, moving in that pattern, all right? Feeding and appending it to t in this case, all right? What you're saying is that you're thinking like the first algorithm we did, where we take one index and compare it with all the rest in this pattern, and we take one and compare with all the rest in this pattern. That's what you're saying, right? Yeah. So here, let me see, I and j will only increment if that condition is true. So let me explain. It means that in this case here, where 2 and 3 is here, all right? Because this was where you landed here, we're going to increment I. J will remain the same. All right? So J will still be at 3, and I will now be at what? 5. We'll now compare again. And we keep, exactly. So we'll keep doing that until it blends out. You get that? So the only time the increment will happen is we're not incrementing simultaneously. We're only incrementing if the condition is true. So if the left index is less than or equal to the right index, perform this. Else, let the right index be chosen and increment j. So I can still be in the first position while j is increasing because we have lower numbers at that side. Does it make sense?
So this is basically merging and sorting.
Yes, yes, yes.
As loose fast as bit memory.
Yes, yes. All right. So let's look at some numerics. Let's look at some numbers, maybe to help us understand it better. All right, so we have the start of our array 6, 5, 12, 10, 9, and 1. All right. If we split that into two, we have 6, 5, 12 at one part there, and the next part we have 10, 9, and 1. So the left hand side we sort. All right, so we pick that split 6, 5, 12, and we have a measure of 5 and 6. Here we have 6 with 5 and 5 and 12. Here we have 6 with 5 and 12, and we compare them 6 versus 5. 6. Let me see. Hold on, let me see something. I'm sure I didn't make a mistake. Just give me 1 minute. Just compare something quickly. Yes. Oh yeah. Okay. All right. So this. Okay. Yes. All right. So if just one thing I forgot to emphasize so that we don't create confusion now. The subarray, which is the merge sort, would arrange that in an ascending order before the merge now takes into consideration. So the first one here, let me just explain that quickly, so that it makes sense when we go to the numbers. What the first part here doing is dividing into 2, then it's now trying to now perform some operation with that 2, and you keep dividing that into smaller blocks until you get some left component and right component that's already sorted. Then we'll now feed that as input into the main merge algorithm that now does the index shift of ij, depending on the condition. So what we're seeing here, is the first half, which is the merge sort. So the merge sort is taking the left component and trying to sort itself in that part. Initially we have 5, 6, 5, 12. When it's done, we're going to have 5, 6, 12. The right part, we have 10, 9, 1. When it's done, we're going to have 1, 9, 10. So when we come into the final merge algorithm, what we're feeding left and right will be 5, 6, 12, which is the left, and 1, 9, 10, which is the right. Then we'll perform the operation of ij switches that gives us the final expression of 1, 5, 6, 9, 10, 12. That's how it works. All right? Is it clear? Question?
So in terms of, so typically when if we want to implement a merge sort algorithm, we use an occasion, right?
If you want to implement what? The merge sort.
Yeah.
We see there's a recursion call there happening. Yeah. So what happens with recursion? It always demands memory, right? Stack keeps demanding because you keep adding to that each time.
Yeah, that's what I wanted to ask. So if you say anything that we can implement recursively, we can also implement using loops.
Yes.
So if I implement like a merge sort algorithm using recursion, and then I implement the same thing using iteration, will that make any difference with regards to the time and the space complexity?
Yeah. Yes. Well, it depends on the number of loops again you're going to have to replace the recursive call.
Okay.
Right. So if you're demanding more loops for one recursive call, you're still going to increase complexity beyond that point. Right. Okay. Any questions? Okay. Huh? Okay. All right. So I'm done explaining to you the concepts in the slide. Now, when you go back and you're looking at that slide and you watch this video, you'll be able to understand exactly what's happening there. If you're almost out of time, but I can at least show you some examples we've created based on what we've shown here. All right. The first example is to find the name of a student in an unsorted list. All right. Here is just the method that has been created for that, and this is a linear search example. All right. So in the linear search example, we have the name of students that will be passed in, or the array of student names that will be passed in. So all we're trying to do here is to run our loop. Notice here is a single loop. And within that single loop, we are saying if it's equals to key, and you can use equals key, the keyword, or you can use equals ignore case. The ignore case gives you a much better option because it ignores whether it's uppercase or lowercase and just searches for the words itself. And once you're done, it returns a I, or returns a -1, or whatever you want to return to signify that it was not successful, right? If we run this, you will see the output shown here. And before I start showing the output, let me quickly show you what the main method is saying. So in the main method here, for example 1.5, we have an unsorted name. So we fill it there, some names there. String names will contain Bello, Ako, and the rest of them. We have string target name. We've chosen it. Notice that I intentionally capitalize some words or some letters within there. All right, so like you see, equals ignore case works. If you use just equals, then it will return a -1 and tell you that it cannot find that specific thing. All right. So in this case, we're looking for this as our keyword, and we feed it to our linear search methods, names, which is the array that has been set, and target name, which is the name of interest, and we're able to print out the information. And that is why you can see here, which is linear search names, and the name in question, it tells us what? The index. Remember, what it returns to us is what? The index, I. What's returning back to us. Okay. Example 1 is done. Example 2 is the binary search option, which is 5.2. So here, find the first occurrence of a fault marker in raw sensor data. So we have some sensor data that returns 1, 2, 5, -4, -5, but we intentionally included one that's -999, so a large number. So we want to be able to see if we can detect what the errors are within that data that we are getting. So here is an example of that, which runs through our loop in terms of our data set array and picks out when a specific log is equal to the marker and returns the index of what that log is. When you run that, you would see that here in this line, it found that index 3. And just to know exactly what index 3 is, if I scroll down to the main file or to the main method, you will see what we used. Here are the logs and the information that was fed as an array in there. The marker we're looking for is the largest value, -999. And when we call our function in this line here, we can print out what the IDX fault is, and that will tell you index 3, which is 0, 1, 2, 3. That position there, where you have the 999. Okay. Now we leave from there and go to binary sort. Let's see. So in the binary search example, we have to locate a student's ID in a sorted array. So in this case, we have a while loop that takes in our low and high. If you remember the algorithm we showed earlier, we set low and high to 0 and the length of a -1. And that's exactly what's happening here, which is 0 and length of a -1. So when we perform the while loop, we run through that loop to check if we've gotten, and how does binary search work again? We find the minimum points. Remember, if it's there, it prints that it's here, much easier. Else, we begin to compare this side by reducing the low, by increasing low, or this right-hand side by what? Reducing the high, all right? And we're able to compare element-wise until we get that output. Now, in our main method there, that'll be 5.3. Here we now have some numbers given. It's already sorted in this case, like we said, for binary search. And if we now find a target which is 1045, we perform our binary search, it should be able to tell us that 1045 exists here, and that points to index 5. So you see 0, 1, 2, 3, 4, 5. We have the 1045 there. All right. So the algorithms that has been shown are probably what you do when you write code, sometimes without even knowing you're performing such operations. All right. All we're trying to do is to bring it to your attention that these things have been classified as a problem set of their own, and you're able to measure the complexity of what they are. Starting by showing you that a loop will create O of n, right? If you're running just one line of code, it's O of 1 because it's one time. If it's a nested value, then the O would be squared that. Then depending on the operations you have, you can have different, and you can have a log n, you can have n of log n, and so on and so forth. All right. So just please investigate what the complexities are. And again, they are the same for whether it's time or space. The only difference is that you must take into consideration what operation you are doing. Do I require more memory than in space? Do I require more time in terms of iterations or loops than it's time? Right? Yes.
The O of log n complexity. I think it's hard to like figure out. Like, I don't understand how they get to that.
When it is halved, there's an example we showed when the case was halved. Yes, when the data set was halved. All right. So I think if you look at the algorithms there, when I update you will see. If you look at the algorithm there, you will see an example of that. All right. Let's just move on. I will jump this quickly and do one that has to do with the merge sets or the merge sorts, the last one, so that you can see every other one. You have access to this slide or to this script. You can actually go through it yourself. After that one, stand attendance, and we're done. All right. Okay. So in our merge sort example, we have int A, which is 85, 32, 57, 21, 90, 13, 68, and 45. We have our B there, which now stands to be like our T in the algorithm that we created earlier on. So all we are doing now is to now try and print out what the original value is. Now print out what the merge sort value is. The original value again is A, but here becomes the merge sort value. So if we run our program, it should be able to perform the given operations and give us the answer. So because of time, you try it on your own. Let me just show you what the output is. If the original value is this, it will perform based on how the merge sort operation has been written and sort that out and give you the sorted algorithm here. You now have 13, 21, 32, 45, 57, 68, 85, and 90. All right. Now, because I've already explained the algorithms extensively in terms of the sort algorithms, there are examples to back it up. So look at the examples. All right. When you go to the slide, you would see. When you go to the slide, you will see that there are other examples here. Each of what is being referred to has either been addressed by us or is something you're familiar with already. All right. I would still advise that you try the examples on the slide and ensure that the understanding has been transferred to you based on what you've done in class and what's in the slide. There's also an example at the end here that you should look at. This was taken out from your textbook. The exercises here. Right. This one refers to the bubble sorts that Alan was referring to earlier. All right. So this is where you now swap them individually. Right. And keep doing that until all of them are swapped. And again, there's a code for that underneath this slide. You can just try in case you're not sure of how to do it. Usually, I advise that you try it on your own. Just try and see how much you know, how much you can repeat. Then you use that. Are we together? Yes. Yeah? Okay. Let's sign the attendance. All right, you have access. Please click on that. Sign in. Turn up.